Welcome back to our course on mechanical behavior of materials part 2. So we have discussed the topic of fatigue, especially for metallic systems, alloy systems. Okay, today we will talk about deformation behavior of composites. So a part of this was already discussed in our previous course on mechanical behavior of materials part 1. If you go through lecture number 45. Okay, and we will discuss more about deformation in composites. Okay, so let's proceed. So as discussed before in our last course, so composites, these are materials consisting of two or more distinct phases which are suitably arranged or distributed. Okay, so you are going to have, whenever we talk about composite, you have matrix and reinforcement. And depending upon the matrix and reinforcements, you are going to have different types of composites. So based on the type of matrix, you can have metal matrix composite, MMCs, okay, then polymer matrix composite, PMC, ceramic, matrix composites. CMCs. Okay. So in MMCs, you're going to have metal as matrix. Similarly, in polymer PMCs and CMCs, you're going to have polymer and ceramics as matrix component. Okay. And again, remember that these have been discussed in our previous course, lecture number 45. I'm just repeating some of those concepts again. And based on the reinforcements, you can have particulate, reinforced composites. Then you can have short fiber or viscous reinforced. Then continuous fiber and laminated composites. Okay, so in particulate reinforced composites, as the name suggests, you're going to have particles. Suppose this is your component or composite, and then you are going to have particles. Okay. So these are your reinforcements. Particles. Okay. Then your road can have let me draw the composite first. Then I will show you the reinforcement. Okay. So the second one is viscous reinforced composite, a short fiber. So you have these fibers which are dispersed in the matrix. Short fibers. Okay. Now you have continuous fiber reinforced. So those will be fibers which are continuous. So if you see in 3D, it was going to look something like this. So it will be continuous. And it is inside, okay? This is one fiber. Then you have another one. Another one. Okay, so it's a continuous reinforced. And this one is short fiber. Okay, so you can understand the difference. Both are fibers, but one is short fiber, another one is continuous fiber. Okay. And the last one is laminated composites, where we have laminates and then they are stitched together. Okay, so these are the four types of composites depending upon the reinforcement, type and distribution of the reinforcements. Now the properties of a composite or characteristic of a composite depends upon matrix. So the constituents. So one is matrix, another one is reinforcement, and the last one is interface. And this is very, very important, interface, right? So we are talking about the material aspect of it. So when you see composites, you have two constituents, matrix and reinforcement, and then you are going to have interface. So if you have this particle in the matrix, then you are going to have interface also associated with it, right? So this is your interface. And the matrix composites behavior is going to depend upon the interface characteristics also. Okay, so this is material aspect. Other than that, you have effect from obviously processing parameters, how these composites are going to be fabricated. Okay. So interface becomes important. Why? Because the load transfer takes place from the interface itself. Right? This was also discussed before. So interface load transfer between the matrix and reinforcement takes place through interface. Okay. Similarly, you are going to have interface for fiber also. If this is a fiber, okay, so you are going to have interface, which is this. The blue one is the interface. And then you have matrix in both the cases. Okay. So you have matrix, reinforcements, and the interface. Okay. So the characteristics of interface is also important when you define the composites, behavior of composites. Okay. So now let's talk about how do you get strengthening in composites. So there are two types. One is direct strengthening and another one is indirect strengthening. So the direct strengthening is the fundamental, part of strengthening in composite, which is because of the load transfer between the reinforcement and the matrix. Okay, so this is due to load transfer from the matrix to reinforcement. Okay, for example, load transfer from fiber to, sorry, opposite, from the matrix to the reinforcement. So from matrix to fibers. Okay, so this is direct. So because of the load transfer uh, from the matrix to the reinforcement. Now, indirect strengthening is you are strengthening the composite because of some indirect method. Okay, so this happens due to change in the matrix microstructure and properties due to addition of reinforcement. So when you are adding reinforcements, say fibers and the particles, you are changing the matrix microstructure and properties somehow, and because of that, you are giving some strengthening to the composite, and that is what it is called as indirect strengthening. Okay, so indirectly you are providing strengthening to the composite. Okay, so I hope you have understood the difference between direct and indirect strengthening. So when we have indirect strengthening, you can have several components. Okay, so you can have organ strengthening, and all these strengthening mechanisms we have already discussed in our part 1. Then grain boundary strengthening. Then quenching or quench strengthening. Work hardening. And have solid solution strengthening. And one more thing is remaining. If you go through the strengthening mechanisms, we had discussed precipitation. Okay, so the precipitation will be valid for precipitational hardenable alloys, precipitation hardenable alloys, right? Like 70752 series alloys matrix, which will show the formation of precipitates. Okay. So, you know, because of the presence of reinforcements, you are going to see all these strengthening mechanisms being activated in the composites, and it is indirectly giving strength to the composite. Okay, so we can quickly go through all of them. Okay, so due to thermal mismatch, okay, remember that matrix has high CT and reinforcement has typically low CT. So there is a thermal mismatch between the matrix and reinforcement, right? And when this happens, you are going to induce strain, right? Thermal induced strain. And this will lead to thermal induced stress. Okay, and this is what we call as quench strengthening. So when you are quenching, because of the thermal mismatch, right? CT mismatch between the matrix and reinforcement, you're going to induce thermal strain. One is going to contract, you know, less than another one. So you are going to generate strain, and which will lead to the stress. So that is quench strengthening. Okay. Now, if this stress is higher than the yield point, what is going to happen? You are going to see plastic deformation in the matrix. Okay. And if that happens, you are going to generate dislocations at the interface, right? So if this stress is higher than yield point of matrix, you are going to generate dislocations at the interface or near the interface. Right? So this will lead to also strengthening. So you are generating dislocations, they are going to interact. So you are actually talking about work hardening here, right? So because of the quenching, you are generating strain, which is leading to stress. And if that stress is higher than the L point, you are going to generate lots of dislocations. Now you have generated lots of dislocations, right? So these dislocations can act as heterogeneous sites for nucleations of precipitates in precipitation hardenable alloy systems, right? Say aluminum alloy we are taking, which can show precipitation, which can form precipitates, right? So these dislocations will act as heterogeneous sites. So what we are talking about now is special case of precipitation hardenable alloy. So they are matrix here. Okay. So the dislocations you have generated will act as nucleation sites for precipitation. Okay, that is point number one. Because of the generation of dislocations. Now the interface itself is going to act as nucleation site, right? Because that is also a heterogeneous point. So interfaces themselves act as heterogeneous nucleation sites for precipitation. So two things are happening because of the incorporation of the reinforcements, right? The first, the interface, because of the reinforcements, they are acting as a nucleation sites themselves, right? Second, because of the CT mismatch, you are generating lots of stress and therefore you are generating lots of dislocations, and those dislocations are also acting as a nucleation site for precipitation, right? And remember the concept of indirect strengthening, you are changing the microstructure or the properties of the matrix, and this is what we are doing using these two, right? Nearby the interfaces, you are generating now lots of precipitates, and this is called accelerated aging. Aging, you know, this is accelerated aging. You are accelerating the aging phenomena because of the presence of the reinforcements. Okay. So if you have, say, reinforcement, because of the thermal mismatch, you are generating lots of dislocations. Okay. Now these dislocations are going to, so this is the concept of work hardening. Now this dislocation, they are going to interact. Now these dislocations can act as nucleation sites for precipitations. And interface, this interface can also act as nucleation sites for precipitation, and both of these will lead to accelerated aging. Okay, so this is indirect streaming, and you are going to see the same thing in fiber info. So in the fibers also, you are going to see lots of dislocations in the nearby regions, and therefore lots of precipitates also in the nearby region. So if I plot roughly say pits density. So pits because of the presence of dislocations, right? H pits you can talk about. And then distance from fibers and particulate. Okay, so we are now counting the number of pits per unit or its pitch density, right? From the distance from the fiber. So if we have say fiber like this, right? So what we are calculating now is the pit density as you move away from the fiber, okay, along this direction. And we also know that pit density is going to be highest near the interface. Okay, so if we plot for different volume fraction, so the first is unreinforced, so the 0% of reinforcement. So we call it monolithic. Okay, so there is no reinforcement. That means the pit density is expected to be uniform. Okay, so it's horizontal line. Now, if we increase the volume percentage, so you have 2% and then say 10%. So all these are rough schematic, 10%, 2%. Increasing volume percent. Okay, so pit density is going to increase as you increase the volume percent of the reinforcement. Okay, and it is the highest near the interface and it goes down as you move away from the interface, and then it obviously it is going to become constant or 10 to 0%. Okay. Now, if we have say different size of the particles, so how it is going to affect the indirect strengthening? So we are talking about indirect increase in yield strength. And here you have volume fraction of say silicon carbide particles in aluminum alloys or not aluminum alloys, aluminum silicon carbide. Okay. So you're going to observe something like this. So this is for 100 micron meter, 20 micron meter, 3 micron meter. Okay, so these are particle diameter. So at a constant volume fraction, if you say we are taking say this particular line at a constant volume fraction, the increase in the indirect strengthening is increasing as you decrease the particle size, right? And this can be attributed to increase in surface area per unit volume. Okay. So as you decrease the particle size, you are increasing the surface area per unit volume, right? So you have more surface area per unit volume, and obviously if you have more surface area, more interface is there. So you are going to increase the strength of indirect strengthening. Okay. Now the another one is grain boundary strengthening. So we have discussed about quench strengthening, then precipitation strengthening, and earth hardening. So now it's grain boundary strengthening, right? So remember, when you cast the composites, you have lots of nucleation sites, right? And those nucleation sites are your reinforcements, right? So those small particles you are adding of micron size, 20 micron, 10 micron, 5 micron, 2 micron, right? So they are going to act as nucleation sites during casting, right? So you are going to have finer grain size of the matrix as compared to if you don't have the reinforcements. And if you have finer grain size, you know that it will lead to more drain boundary strengthening because of the Hall-Petch relationship we have already discussed in course 1. So presence of particles can act as nucleation sites for solidification during casting. And if that happens, you have more number of nucleation sites, right? In fact, if you increase the more number of or volume fraction of the particles, so this will lead to decreasing grain size and therefore increasing strength. Okay. And if you plot, grain size versus volume percentage, what will happen? If you increase the volume percentage, you have more number of nucleation sites, right? So you have finer grain size, right? So your grain size is going to decrease of the matrix, right? So increasing the volume percentage is going to increase the strength of grain boundary strengthening because of the much finer grain size because of more number of nucleation sites. Okay, and this is happening because of Hall-Petch. Okay, now we are left with organ strengthening. So these particles are hard and non-shareable. So what is going to happen? You are going to see bypassing of dislocations, right? And then if you remember, we had discussed this formula in organ looping, right? So if your precipitate size is larger, when we are discussing about precipitation strengthening, so if your precipitate size is larger, you are going to see the organ strengthening, right? Or organ looping. Dislocations are going to bypass, right? So same thing is going to happen. These are hard and non-shareable particles, these reinforcements, right? So dislocations are going to bypass. So you can nicely have this formula where G is your shear modulus, B is your Burgess vector, and L is the distance between particles, right? Two reinforcements. But these are not very effective here. Because the particles are very large. But if if you have fine particles, very small particles, then this can be also effective. Okay. And then we have solid solution strengthening. Again, this is not very effective way of indirect strengthening. So reinforcements may affect microsegregation. Okay, as a result of solute segregation at interface or chemical reactions with the matrix. Okay. So if this happens, the content and distribution of solutes in the matrix have changed, and this could lead to the indirect strengthening. Okay. So what is happening? You have the reinforcements, right? And they have interfaces as we have discussed. So solutes can segregate, okay, at those interfaces. So these can lead to the solute changes in the matrix, right? Solute content and distribution. Second, you can get the chemical reactions between the matrix and the particles themselves, right? And if that happens, you are going to also change the solute content and distribution, especially near the interface, right? And that way you can indirectly enhance the strength. Okay. So we have discussed all different type of indirect strengthening mechanisms, right? Starting from quench strengthening to work hardening to drain bond strengthening, organ strengthening, solution strengthening. So main is their quench hardening and this work hardening. They are the most important indirect strengthening as far as reinforced particles are concerned. Discontinuous reinforced particulate metal matrix composites are concerned. Precipitation strengthening is also important if the matrix can show precipitation strengthening. Right? That also becomes important. Organ strengthening is not that significant because the particle size is slightly higher, but it can give some strengthening if the particle size is reduced dramatically. Okay. So overall, if I write delta sigma, which is the increase in strength because of the uh, presence of the reinforcements. So you are going to have direct contribution as well as indirect contribution. So you have sigma direct, and then you are going to have indirect contributions, right? So you have sigma quench. So this is quenching, a quench strengthening. Then you have delta sigma organ, then delta sigma work hardening. Okay. Then you are going to have delta sigma precipitation strengthening, and finally delta sigma solid solution strengthening. Okay. And these all are part of indirect strengthening. Okay. So this is how a composite is going to get strengthened because of the presence of reinforcements, either direct or indirect. Okay. So I will stop here, and in the next lecture, we will talk about the tensile behavior as well as fatigue behavior of composites. Okay. Thank you.